Okay, thank you all for coming to the last session of the HDX workshop. So today the plan is to cover a different definition of expansion called Coboundary expansion and some of its applications. So in the first talk, I'll be talking about applications to direct product testing. And in the second talk, Chinmay will cover some applications to quantum codes. So the first part of the talk, around 10 to 15 minutes, I'll define and motivate Coboundary expansion and give some examples of it. Okay, so let's recall what a simplicial complex is. We have a set of D-uniform hyperedges over n vertices, and then we take this downward closed picture where at the ith level, we put all the I sets that are contained in any of the hyperedges, the D-uniform hyperedges. And today we saw local spectral expansion that Max defined. And today we'll only be looking at a two-dimensional version of Coboundary expansion because that itself is sufficient to give very nice applications. So let's see what this is. So think of a graph which is given by the vertices and edges of your simplicial complex. And it also will have some triangles in it because of the triangles in the simplicial complex. And now consider any 2 XOR instance on G. So this means that you label the edges of G by 0 or 1. And you consider the 2 XOR instance which corresponds to this labeling, which is just you put in the equation xa plus xb equals 0 for this edge, and so on. And now a natural question is, when is this instance satisfiable or not, right? So does this instance, can anybody look at this and say whether it is satisfiable or not? Okay, so that's great. So this is exactly the answer I was looking for. So this, if you look at this triangle, it sums, the edges sum up to, this triangle, the edges sum up to 1. But if you looked at the corresponding triangle equations here, the LHS always sums up to 0. So it can, in a 2 XOR instance that is satisfiable, you must be locally consistent on all triangles. Okay, so this instance is not satisfiable. So the next question is, what if you are given an instance which is locally consistent on all triangles? Does it need to be satisfiable? So any answers for that? Okay, so in general, I can see many no's. So in general, it may not be satisfiable even though you are locally consistent on all triangles. But it turns out that for this graph, whenever you are locally consistent on all triangles, you always have a satisfying solution. But you can ask a more robust version of this question, that what if your 2 XOR instance is locally consistent on most triangles? Do you expect a satisfying an assignment that satisfies most edges? So this motivates the definition of a coboundary expander with parameter C, which says that if you take any 2 XOR instance on this graph G that is locally inconsistent on only epsilon fraction of the triangles in G, then there is a vertex solution that violates only C times epsilon fraction of the edges. Okay, so any questions about this definition? Okay, and note that even though it's true for this G, it's in general not true for all graphs. In fact, we believe that, in fact, there are instances where you have a large gap between the fraction of locally consistent triangles and the fraction of edges that you can satisfy. So these are really very special types of graphs. Okay, so why on Earth is this called expansion? So one reason is, as we saw in Max's talk, we should look at properties that the complete complex has and try to generalize them to sparse complexes. So let's check that the complete complex is a coboundary expander with, in fact, constant equals 1. Okay, so let's say this is Kn with vertices Vi, V1, etc. And the goal is to show that this is a coboundary expander. So suppose you are given an epsilon locally inconsistent instance of 2 XOR. The goal is to find an assignment that violates at most epsilon fraction of the edges. And the way we'll show that such a assignment exists is just by giving an algorithm to find such an assignment. And what we can do is to get a randomized assignment. So pick a random vertex Vi and assign it to be 0. And then just propagate this value according to the edges touching Vi to all the other vertices. So we assign Vi to be 0, and then V1 must be 1 because this edge needs to be satisfied, and so on. So while assigning the other vertices, we don't care about the edges that are contained within the other vertices, only about the edges from Vi to the other vertices. And now let's try to see what is the fraction of violated edges, because you might have violated some edges here while you assigned the vertices. Okay, so one easy observation is that an edge is violated if and only if it's part of some inconsistent triangle. So for example, if you take the edge V1, V2, it is not violated, whereas the edge V1, V3 is violated because it's part of the inconsistent triangle VI, V1, V3. Yeah. Yeah, because this is a complete graph, it's even simple. Yeah. So you just need to pick a vertex and use the edges for propagation. Yeah, but in general, you would use like a spanning tree. Okay. Yeah, so analyzing this is pretty easy. So the main observation is just that an edge is violated if and only if it's part of an inconsistent triangle. And the expected number of violations over all assignments is just going to be the expected fraction of inconsistent triangles, which we know is epsilon. So you have found in expectation, you know that there exists. So yeah, there exists an assignment that violates only epsilon fraction edges. So this proves that the coboundary constant is 1 for the complete complex. Okay, and I will leave this as an exercise for you to generalize coboundary expansion to 1 dimension and show that it is actually equal to the edge expansion in the graph, or the Cheeger constant. Yeah, that's an exercise. But it's going to look something like you'll have functions over the vertices. So you'll have like 2 XOR values over the vertices that are consistent on edges. So they sum up to 0. Yeah, so they must be a lifting of the all constant function, like all zeros or all ones. And that exactly would give you the definition of edge expansion. Okay, any more questions? Okay, so now let's see why this definition is even different from the definitions we've already seen, because otherwise it does not make sense to have another definition. So let's see 2 examples. First is a union, just a union of triangles. Again, you can just use a similar argument to show that it is a coboundary expander, but of course it's not a spectral expander. And on the other hand, if you take a random graph, it does not contain triangles. So whatever 2 XOR instance you take on it will always be consistent on all triangles. So vacuously, it's not a coboundary expander, but it's a spectral expander, at least in one dimension. And there are more complicated complexes which are local spectral expanders, but not coboundary expanders. Yeah, so if you take any 2 XOR instance, it's vacuously consistent on all triangles because there are no triangles. Oh, yeah, but it's not going to be. Yeah, it won't be satisfiable. Okay. Okay, so now let's see examples of graphs which are both coboundary and spectral expanders, because we want to kind of, yeah, it's not good enough to be either one of them for some application. So firstly, we already saw the complete complex in Max's talk that it is a local spectral expander, and we just showed it's also a coboundary expander in 2 dimensions. And it turns out that even these spherical buildings that are, slightly less denser than the complete complex, they also, and they were defined in Yotham's talk, these are also coboundary expanders. And in fact, you can use a similar propagation argument to show this holds. And then very recently, Chapman and Lubotsky constructed the first sparse family of even just graphs, like 2-dimension graphs with triangles, which are both spectral and coboundary expanders. So these are based on these quotients of affine buildings that Yotam talked about. So in fact, we don't know of other examples which are other sparse graphs which are both. And let me just say that proving coboundary expansion, we just have a few techniques to do that. One technique is called the Cohn's method, which is like some generalization of this propagation argument that I just showed you. And then this works for dense graphs which already have a lot of triangles. So it's easy to analyze the propagation. You can show that the propagation algorithm is sufficient to find the solution. And then for sparse graphs, we have so-called local to global methods that work to show that they are coboundary expanders when they have a nice structure in the links. Okay, so this talk is not going to be about proving coboundary expansion. So next, let's move to the applications. So I will first talk about the problem of direct product testing, and then tell you about how we can get size-efficient constructions via these coboundary expanders, and then finally discuss some proof ideas of why coboundary expansion helps. So before that, are there any questions on the definition? Yeah. Yeah. So yeah, for 2-dimensional coboundary expansion, we just look at the base graph with, it already has a lot of triangles, so we can ask whether it's coboundary. And in fact, today we'll only be looking at the base graphs. Okay, any other questions? Okay, great. So let's define direct product testing. Okay, so this was actually defined by Goldreich and Safra in '96 in a way to, kind of simplify PCP constructions and the parallel repetition theorem. Okay, so let fix some set system over N. This, let it be like this K uniform set system. And the direct product encoding of some function on n from the universe n to 0, 1 using this set system is simply the restriction of f on the sets. So you can also alternatively think of it as a huge table where in each entry of the table, you write down f restricted to t. So each entry contains a k-bit string. And the next natural question is, given such an arbitrary table, can you locally test whether it is actually close to some direct product function? Okay, so let's say you have some arbitrary table h of t. You want to test whether it is equal to direct product encoding of some function. So you can perform a natural two-query test, which just picks two sets, Ti and Tj, and just tests whether h of Ti is equal to h of Tj on the intersection. Okay, so this is clearly, this test is clearly satisfied, like it's passed with probability 1 by every direct product function. So the question is, when this test passes, can we say something about the structure of H? Okay, so what we want is that if this test passes with some probability, there actually does exist some f for which probability that h of t is equal to f restricted to t is proportional to the probability that the test passes. Okay, so to formalize this, we'll say that this test has error epsilon if whenever the test passes with probability epsilon, then there exists some function for which the probability that h of t is equal to f restricted to t is at least epsilon to the 6. So I just chose an arbitrary polynomial of epsilon here. Okay, so any questions about the definition? Okay, so the goal then is to find a set system so that whenever you do this direct product test on the set system for any arbitrary h of t, you have that this has, this direct product test has small error. Yeah, so roughly, so this is the parameter that works out when you take the complete set system, which I will just talk about. And the intuition is that you want a small enough parameter so that these sets have some kind of expansion. But you don't want it to be too small so that, I mean, then it won't be meaningful that the test is passing. Yeah, so so I will mention this application, for example, to parallel repetition. It's easier to prove parallel repetition theorem when you have like root k, but with some losses. Yeah. Oh, okay. Okay, any more questions? Yeah. So error in some sense is like the smallest epsilon for which whenever the test passes with probability at least epsilon, you have that probability of h of t is equal to, is also at least epsilon to the 6. Yeah, so for example, we'll see tests where it has error 0.99, but when the test passes with probability half, you can't say anything about the function. So it does not have errors like half, let's say. Okay. Okay, so let's look at the complete complex, which is our running, first example as a sanity check. And here, Noor and Goldenberg showed that if the direct product test on S has error, which is, even just polynomial in 1 over k. So that just means, again, that whenever the test passes with any epsilon, which is larger than poly 1 over k, then there does exist a global function for which, H is correlated to this global function. Okay, so this set system has size n to the k. So a natural question is, can you get the same guarantees or similar guarantees with a sparse set system? Okay, so this is exactly what Noor did. So she showed that if you have an expander graph, and you take the set systems of all the vertex neighborhoods in this expander graph, so fix some radius 10, and let's say you take the 10 diameter neighborhoods of every vertex. So this is a set system with n sets. Then this has error 0.99. And this is for a usual spectral expander. And this was the key ingredient in her proof of the PCP theorem. And I'll talk a bit about how direct product tests actually imply something about PCPs a bit later. Okay, so the natural question is, can we extend the direct product test using the same, is there an issue with the analysis, or does it have some fundamental other issue? Okay, so Bogdanov showed that if you're given a generic spectral expander G, then the set system, which is the vertex neighborhoods of G, has error which is at least half. So in the sense that you can build a function which locally, which passes the direct product test, but there is no global function agreeing with the h of t, the local function. Okay, so let's just see a quick proof of this. It's not very hard. So our aim is to create a counterexample which passes the test, but there is no global function. So let's look at a spectral expander, and we are going to build functions on every neighborhood of every vertex. So the function will just be a two coloring the set. So we'll build a list for every vertex. Instead of building one function, we'll just get a list of two functions, which is just going to be the two coloring of its neighborhood. Okay, so there are two colorings of every neighborhood, and you can assume that the spectral expander is tree-like, so there's a valid two coloring of every neighborhood. Okay, and then our H will just be to randomly pick 1, 2 coloring from every list. Okay, so this H of this H that we have built, we can show that this passes the test with probability half. So why is that? Because now if you take any two overlapping neighborhoods, together they form a tree. And with probability half, you would have picked the correct like U and V to be consistent labeling. So overall, this is a two coloring of the neighborhood of U union neighborhood of U. And that's exactly what the direct product test is testing. Okay, but any global function that you will build needs to be a two coloring of the whole graph, because it must be consistent with every two coloring in the local neighborhoods. And a generic expander is not two colorable. In fact, we know that there are graphs which are far from being two colorable. So the max cut in such graphs is like half. So you can show, so I won't show this, but you can show it that every function will have this agreement with the local functions being very, very small. Okay, so any questions about this? Yeah, so you define the test as like taking picking U and V, which are, let's say your neighborhood size is like, neighborhood radius is 10, then you'll pick U and V with distance 5 or something. Yeah, yeah, I'm kind of ignoring that. Okay, so any other question? Okay, so this, let's like kind of try to abstract the issue in this so that we'll come back to it later. So the issue is that we could build these lists on every vertex for which these lists are consistent. Like if you take list of U and list of V and looked at them and on their intersection, they are equal. But there's no way to, pick one string from each list, which is consistent on all the edges. Okay, so this is something like the lists are consistent, but there's no way to, disentangle the lists. Okay, so now let's see how Coboundary expansion helps us avoid these kind of issues. So firstly, you might think that, what's a natural set system, given that this is a, workshop on HDX. So a natural set system is just to take S equal to the K sets in your HDX. And that's exactly what Dinur and Kaufman did. And they showed that this direct product test on S, whenever you have a local spectral expander as defined by Max, this has error at most 0.99. Yeah, so again, this is a recap of what that means. So basically, there's a global function such that you can, lift it. F, H of t is F restricted to t for most sets in XK. Okay. Sorry, which parameter? Yeah, this is like with probability 1 minus del. Yeah, okay, sorry, I just wrote it in the opposite thing. But for all EPs, yeah, so in this 99% regime, you can get like stronger guarantees. So you can, okay, sorry, actually it's the same guarantee. Yeah, it's the same thing. It's just that you can rewrite like 1 minus delta to the 6 is 1 minus O of delta. So, yeah. Yeah. Okay. So they conjectured that there are HDXs which are sparse, and the direct product test on XK has error small. So small error, which is like any small constant 0.01. Okay, so what we showed also with Dickstein Dinur is that this direct product test in 1% regime, local spectral expansion is not enough. So you need this additional notion of Coboundary expansion. And in fact, this proof is a generalization of Bogdanov's proof. So you might have thought that, just adding triangles to your graph will make it work. But in fact, if you just added triangles without having Coboundary expansion, you still cannot solve get soundness for the direct product test. Okay, so what we showed is that, in fact, if you have this one additional property of Coboundary expansion, then you do get error, so less than 0.01. So in some sense, Coboundary expansion is, necessary and sufficient for direct product testing. Okay, so this, along with, variance, we required some variance of the Chapman-Lubotsky complex, and to show that they have all the sufficient parameters for the soundness to work out. This does imply that there are set systems which are sparse. So size is O of n, where this direct product test has error 0.01. So these will be complexes X, which are both local spectral expanders and Coboundary expanders, only in 2 dimensions. Oh, so that's a great question, and that's like one of my open questions in the end. So we don't know how to efficiently test it, but we can prove Coboundary expansion for these very special complexes because they have like a lot of structure in the links. So yeah, going back to what Yotam had discussed, these links will also be spherical buildings. So using this structure, you can prove that they are Coboundary expander. Yeah, so that's also a great question. So we only use 2D, and actually these complexes, I don't know, do we know that they don't have 3D? They may or may not have 3D. So they only seem to have like, at least, yeah. And yeah, we don't know applications of higher dimensional Coboundary. Okay, so let's just quickly look at an application like why direct product testing implies PCPs. So this was implicitly, done by the Noor, and then later on, IKW used this kind of direct product test to give, much simpler or combinatorial proof of the PCP theorem with like worse parameters. Of the parallel repetition theorem. And then we also used it in our PCP. So really, it's like a very, black box connection. So if you don't know about what 2 CSPs are, you can ignore this slide for a minute. Okay, so suppose you have a constraint satisfaction problem where on this graph, so all the edges have been labeled with constraints, and you're given that this value is at most 0.99. Then you can construct a new constraint satisfaction problem on a larger graph, which will have value 0.01. So that new graph is just, the vertices will just be the, the K sets in this HDX, given by X. And then the edges are going to be if these K sets overlap in square root K. Okay, and now your constraints in the new 2 CSP will just check the obvious thing. So a constraint on T1 and T2 will just check whether T1 and T2 on the like the assignment that the prover gives you on T1 and T2 is consistent on the intersection, and it satisfies all the edges of T1 and it satisfies all the edges of T2. This is very similar to, yes, this is exactly what like parallel repetition would do. And now we can try to use the direct product test to prove that this value is smaller than 1. So assume that this value is not smaller than 1. So this, there is an assignment with value greater than 1, let's say. This will, because it has value greater than 1, it means it also satisfies these consistency constraints, which is exactly the direct product constraints. So this implies that the direct product test, the assignment h of t passes this test with probability at least 0.01. So using the error guarantees of the direct product test, you can get that there is a function on the vertices that is consistent with h of t on a large fraction of t's. And this, with some simple spectral expansion implies that this function f actually satisfies most of the edges of G, of the original 2 CSP. So you have reduced a function with value at most 0.9, at least 0.99, which proves what you wanted, like an error reduction in the PCP. Okay, so this is like, yeah, it's very neat connection to PCPs. Yeah, so the alphabet does blow up to sigma to the k, like it blows up exponentially. But yeah, these like in all these papers, you think of k as a constant. You just want to go from some large constant to some small constant. Okay, so now let's look at why Coboundary expansion gives us this low soundness error, low error in the direct product test. Okay, so instead of looking at very low error, I will just actually give you some idea about the half error case, because that itself we saw that spectral expansion is not enough to get half error. Okay, so this is the idea. The way we saw in Bogdanov's example, there were these lists which were consistent but not globally consistent. So we'll kind of, run this in the opposite direction. So first we'll form lists on a large D. Let's say your function sits on K sets. This function which passes the direct product test, let's say with probability half. So this sits on K sets. You look at some large D sets above, like for D much bigger than K. And for each D set, we will construct a list of, this list will be of size 2. Again, the list will just be, for this D set, you look at all the sets, all the K sets contained within that D set. And that is the complete set system. So we know that, that whenever that passes the direct product test, there is actually a global function. And because it passes the test with probability half, there could be 2 global functions. So you can list decode and get 2 global functions on every T set. Yeah, so because the test passes with probability half, there can be 2 global functions where one global function agrees on half fraction of the universe and another would agree on half. Yeah, so you don't know which is going to be there in your final global function. So we'll just pick both of them in our list. Okay, and in this way, we'll construct a list for every D set above. And then it requires some work, but you can show that these lists are consistent, which means that now if you take 2 lists which intersect in like square root D, so their size is D, so you'll take like square root D intersection, you'll take 2 random Ds which intersect in square root D, and then if you project these 2 lists to the intersection, they will be equal or almost equal with probability 0.99. So yeah, I will not really give the proof of this, but it's kind of, yeah, it's not hard to imagine that this is true. Okay, and try to keep the Bogdanov example in mind. So instead, let's just look at when the lists are consistent with probability 1, which was the case in Bogdanov's example. Okay, so now we will look at how Coboundary expansion can help us pick one function from every list and then find a global function using that choice. Okay, so we'll, instead of looking at Coboundary expansion of x1, x2, x3, we will actually, consider a slightly different graph. We'll look at the graph, which has vertices being x2. So every vertex here is an edge in the complex, and 2 edges are connected if they form a 4 face in the complex. So A, B, C, D is going to be a 4th leak in X. Okay, so first you can create lists on the 6 faces. So let's say you just project the list on the D faces to the 6 faces. So you can do this in a consistent manner because all the lists agree with each other on the intersection. So it's possible to actually get a unique list on the 6 face by projection. So let's say this list is 0, 0, 0, 0, 1, 1, and then the flip of that. So these two functions have distance 1. And then you can further project this list onto x2. So on every edge, you will get a list of size 2 with like 2 length strings. Okay, and now using this, let's create a 2 XOR instance on this graph. So firstly, so the 2 XOR instance will just be how do you, concatenate these lists? Like, do you concatenate them with 0, 0, like the first function in each list, or do you flip the list and concatenate them? So if you flip them, for example, in 0, A, B, and E, F, you will have to flip them. Like the true list on A, B, E, F is like 0, 0, 1, 1 with 1, 1, 0, 0. So you will put in the constraint 1 on the edge. So the constraints capture how you should concatenate the lists. Okay, and you can observe that all triangles in this instance will be consistent. And this is just because, the triangle actually corresponds to a list on the union of the lists. Okay, so now we have the setup for Coboundary expansion. If you assume this graph is a Coboundary expander, then if all triangles are consistent, which they are, you can actually get a vertex assignment that satisfies all the edges. And okay, so then you can just pick one element in each list accordingly. So first you get this vertex assignment, let's say 0, 0, 1 to the vertices. So 0 tells you that you should pick the first element, and 1 tells you should pick the second element. So you'll just say that AB, you should assign 0, 0 to AB, 0, 0 to CD, and 1, 1 to EF. Okay, so now to get a global function, because we are in this probability 1 regime, can someone see how you would get a global function to the vertices, given this function to the edges? Yeah, so you can just project it and everything will be consistent. So for A, you can just pick the value 0. For B, you'll pick 0. E, you'll pick 1. F, you'll pick 1, and so on. And everything will work out. Yeah, so I haven't done the analysis, but everything is just, we haven't done anything weird in this process. So this, when the lists have this consistency property with probability 1 and you have Coboundary expansion, then you can simply project it to vertices and pick this global function, which will be consistent with the list. Okay. And in the general case, when you don't have list consistency with probability 1, but let's say only with probability 0.99, then you can, okay, sorry, there's a typo, but you can, we get that this direct product test passes with probability close to 1, and then you can use the Dinur-Kaufman result on HDX to get a global function. Okay, so finally, let me just say a few words about how you would extend this to low error instead of error being half. So error at half, we needed to stitch together lists of size 2. At error epsilon, we need to stitch together lists of size 1 over epsilon. And this reduces to Coboundary expansion over the symmetric group, which I didn't define. But it's a very analogous definition. You can take this, instead of taking 2 XOR instances on G, you can take unique games instances on G, which label every edge not with 0, 1, but with permutations. And permutation would be like the triangles would be consistent if the permutations product to identity. And then you can define a similar notion of expansion with respect to unique games. Whenever the instance is consistent on most angles, there's a labeling that satisfies most edges. And yeah, and the same proof that we did, we would instead, have find a unique games instance, use Coboundary expansion in this way, and then find a global function. Okay, finally, let me end with some open questions. Coboundary expansion is a very newly introduced to the TCS community, I would say. So there are a lot of open questions. Firstly, one very interesting question is, does it extend, does it play a role in other low degree tests which have been used in, these traditional PCP constructions like plane versus plane, etc. This question, it says that can we efficiently check whether a graph is a 2D coboundary expander. So being a 1D coboundary expander is just equivalent to edge expansion. So we have, a spectral certificate. You can just use Cheeger's inequality. But for 2D coboundary expansion, we really don't know how to do this efficiently. And, so currently we have this one construction and some variants of it, of Chapman and Lubotsky. So can we have other constructions and other applications, coboundary expansion? Thanks.